Okay, cool. So welcome to part B. Let's go dive straight into part B. So the first concept is the notion of the interior, So the interior, giving a topological space and a subset of the underlying set X, the interior is nothing more than the union of all open sets that are contained in A. Okay, so more formally, it's something like this. Okay, so is all the open sets that are contained in A. Okay, so the open sets, for those of this is the 10 open sets, meaning they are part of the topology, right? Okay, so the interior is actually the largest because it's a union. Obviously, it's the largest open set contained in A. Okay. Another thing you need to notice is that in some books, I'm not sure what the reference book, material book uses, Mancres, but sometimes they use this notation, this thing to denote the interior. It means the same thing. I'm using this because I think it's much more cleaner. And here's the first challenge for you. The first proposition is this. You can see the interior has some nice properties. For example, a point is in the interior if and only if there exists a neighborhood of P that, remember, we denote like NP. So this denotes that N is a neighborhood of P such that N is contained in A. Okay, and it has also some other properties, nice properties. Okay, so I claim that this is very easy for you to, this is set theoretic stuff, really. This is like kindergarten stuff. You will be able to solve this. Okay, and another thing I recommend you, I wanted to do it, but then not just because I was lazy, but I think it's also helpful to you if you start drawing things, just look at the name interior. Interior means inside, so try to draw this picture of the interior by yourself to try to give you some intuition. Okay. Okay. Another concept related in some way, as we'll see through the upcoming stuff, is the closure. Okay. So the closure is the intersection of all closed sets containing A. Notice the difference between the closure and the interior. Okay. Whereas the interior was the open sets contained in A, the closure is the intersection of all closed sets that contain the subset A. Okay, so more formally, it's something like this. So it's indeed it's the smallest closed set containing A. Okay. And another thing also you should notice is some authors, they use this notation instead of this. I'm using this because, I think it's much more cleaner. Okay. Okay. And I have another proposition for you. I also claim that this is a kindergarten stuff, just with the set theory stuff. You should be able to prove this. Hopefully I didn't make a mistake. I don't think I made. If I did, it's actually good for you, so you can point it out to me later. And again, I challenge you to draw, to try to draw pictures. Okay. Now at this stage, let me check the chat because, okay. I hope everyone is hearing me, right? I'm still online. Yeah. Type 0 or sorry, type 1 if yes.
Yeah.
Okay, cool. Thank you, Soham. Okay, so that's the notion of closure. Okay. And then we have the notion of exterior and boundary, Again, just look at the name, exterior, outside, boundary, So the boundary formally is defined like this. The exterior is defined like this, sorry. So giving a topological space, and again, a subset of X, the exterior of A is defined like this, as the complement of the closure. Okay. So you know what this is, it's defined like this. And then the exterior, you just take the complement of it, okay? So another alternative convention and notation is to use this, but again, I'm just using this because it's much more cleaner. And then the boundary of A, just listen the boundary. This is where again I recommend you to draw pictures. Boundary. So the boundary is defined like this. We can define it like this. as the complement of these two guys, the union of these two guys. Now the question is this definition equivalent to this? In other words, is this equals this? Well, you can try to find out by going through usual set theoretic operations to see if this is equals to this. Okay, and another thing to add to the confusion or to tend to the challenge, whether this is true. These two guys, these two things here, these two statements. Okay, you don't have to answer now. This is like one of the challenges. You can ping on Discord, and so on. And here's another proposition. I also claim this is very easy for you. This is kindergarten. Again, it's like set theoretic stuff. And if I made a mistake, it will be happy. I will be very happy if you point it out to me later. But I'm pretty convinced I didn't, even though I was rushing to do the slides. It's I claim anyway. This is very easy for you. Okay. So we have the concept of interior, closure, exterior, and boundary. Okay. These are very important. They will show up later. We will come to this later in the metric topology and also in the manifold section. Okay. Now, before I go to continuous map, let me see. Let me check the chat. Does no? It's just a notation. Actually, this CJ is asking whether this thing has anything to do with the thing. It's just let's say it's just a notation. The thing. It's an unfortunate notation. Actually, I was tempted to not use it. It's more of something that I would use, for example, in algebraic topology when we talk about the boundary maps and these things. Yeah. So let's say it's just a notation anyway. Okay. And now let's go to the notion of continuous maps. Okay. So given two topological spaces, right? This is the first one, X and T1 and Y and T2. So with two topologies, a map F from going from the targets from the domain X to the target Y is continuous if for any open set in the target space's topology, the pre-image of that open set is open in the domain space. Okay. Remember set theory 101. This is how pre-image is defined. Okay. So if you the thing you don't remember what a pre-image is, here's a definition of it. This is like set theory stuff. Okay. So F is continuous if whenever you pick an open set in T2, the pre-image of that open set is also open. Okay. So this means under a continuous map, the pre-image of any open set in the target topology is an open set in the domain space in respect to the chosen topologies. This is very important. You will see in a minute in few slides or whatever, or 2 slides. The choice of topology is very important. A map might be continuous under these two topology, but if you change the topology, it might even be, you might even give it from a set theoretical point of view, the same prescription, but then because the underlying topology has changed, it might not be continuous. Okay, so that's very important to note. Continuity depends on your choice of topology, both on the thing, on the domain, and also on the target. Okay. Here's a bit of confusion here, a notation for you to be careful. In a lot of books that I've seen, they kind of use this F-1 instead of this. So, but the problem with this is that it might give the wrong impression that F has to be invertible. So a continuous map has to be invertible. This is not the case. So a continuous map doesn't need to be invertible. Okay, so that's why I prefer to use this notation. Okay. Okay, so here's another challenge. This is not for you to answer. Again, we can discuss this on the Discord. Is whether the pre-image. So we have seen that the pre-image of any open set is is open, the question now is if the pre-image of any closed set in the target space is also closed in the domain space X. Okay. So now here's a question that I would like to ask. Those of you who have been given the notion of continuity through analysis, for example, isn't this definition of continuity much more simpler? Because all you have to do is identify the topologies, right? You know where the open sets in both spaces are. You just have to double check. What do you think? Who thinks this is more complicated than the deltas and the epsilons from analysis? Nobody. Okay. Who thinks it's very abstract? Yes, I agree with George. That's the word exactly. It removes the epsilon delta clutter stuff. Okay, we will come across epsilons and these things in the metric topology in some sense. That's one of the reasons I'm introducing continuity here. So you know it removes all the clutter that George is just saying on the chat. Okay, a bit abstract, but you get used to it. You know, it's all about the topology you are given. You know, most of the time, actually, as you will see in the metric topology, a lot of the topologies that are useful to to physics, to other branches, applied branches, they are other people already built those topologies. So it's not like you have to construct them from scratch yourself. It's just you need to be aware of them, or how to put the pieces together. Okay, so that's the notion of continuity. Now, for most of you that are coming from analysis, this is how you normally, the notion of continuity goes as follows. You know, you say F is continuous at point P when it satisfies blah, blah, blah. And then you say F is continuous if it's continuous at every point P. The question is, can we, instead of this abstract definition through the open sets themselves directly, could we start like this, defining continuity at a point P, and then generalize it to the entire space? Yeah, the answer is yes. And here's the way you do that. Here's the definition here. I'll leave it to you. So F is continuous at a point P if for any open set in the target space whose image of P is also there exists an open set. That's why, so this open set is in the domain space. That's why I'm labeling it OX, okay, in the first topology, such that the point is on that in that open set, and the image of that open set is contained in the Y open set. Okay, so and so this is continuity at P. So you can then say F is continuous if it is continuous at every point in the sense of this definition here. And you can bridge the two, this definition and the previous one, through this proposition that I will leave it for you guys to try to prove. I think it's this is also easy. It might be like tedious, but it's easy. So that F is continuous as per the abstract definition. Let me go back. Is continuous in this sense if and only if it is also continuous in this sense. Okay, that's what I meant with this. Okay, I hope it's not that confusing. Sorry, but yeah. So in essence, you have two definitions, two equivalent definitions of continuity. Okay, you use the one that that's less confusing to you. That's much more easier for you to grasp. Okay, so you have options. Okay, and now let's see this bit of challenge here. First of all, I'm sorry, I was doing this graph is a little bit too small. Can you see properly? Soham, are you able to see this thing, for instance?
Yes, I can.
Okay, yeah. So here's a kindergarten challenge. This is a very simple challenge. The first one is that given any topological space, is the identity map continuous? well, I will help you on this. I will say, yes, it is continuous. You know, you should be able to prove this also. This is very easy. So the identity map is indeed an example of a continuous map, okay? And here's another one. Another challenge is, so consider this two topological spaces where the first topology is the discrete topology, so is the power set, okay? And then the second topology can be any topology, okay? The question is, if it's true that any map that goes from X to Y is continuous. Yeah, you don't need, I will not help you on this. This is like a home challenge. The same with this one here, because this is very easy. You can see this. And this actually highlights, I can guarantee you that at least one of them is continuous, but there's one that's not continuous. Yeah, you have to find out, okay? So you have the space made of alpha 1, alpha 2, okay? The first space X, and you have a space Y made of beta 1, beta 2 with the respective topologies, okay? Remember, continuity have to do with your choice of topologies, okay? If the topology changes, from a set theoretic point of view, the map might not be continuous if you change the topology, okay? I think this example actually illustrates that, okay? So we have this map that goes from the first one, F, that goes from X to Y, and it takes alpha 1 to beta 2, alpha 2 to beta 1. Why not, you know? So the question is if this map is continuous, okay? Well, again, you go and check which definition is best for you. Let me go back again. Is it the first one? This one is easier for you to see. Personally, I would think for that example, this one is much more easier to deal with, to use in order to check if this map F is continuous, okay? And then the question is, what about if we the other way around? You can see it's the same sets, okay? We just changed the arrows, right? Inverted them. So the question is if G is continuous, okay? So I will leave this to you as a challenge. Again, you know, let's see how you do on Discord. Let me check the chat. Is there any confusion about continuity in both definitions? Who found the first? Which of the definitions from the first definition and the second one? Which one do you prefer? Who prefers the first one? I don't see any activity on the chat. Is that me, or is just because no one is writing? Okay, so Stefano likes the last. Okay. Okay, well, you can use that. Yeah, good. And actually on that, this is not the end of it in terms of continuity and all this stuff. We will come back to this later in the metric topology section when you can actually, you know, we have like a concrete, useful continuous maps, some of which you already, you know, encountered in your analysis or calculus course. So you will be able to build a better picture, okay? That's one of the reasons you can see why I want to get out of the general topology stuff to go to much more useful to the metric topology section, okay? So that's all to do with the continuity. Now, a very important concept is, sorry, I forgot actually, there's a challenge for you. A very important properties, some of the properties of continuous maps. So the composition of two continuous map is continuous, okay? So if you have three topological spaces, you know, this one, and this one, and you have, you know, F that goes from X to Y and G that goes to Y, from Y to Z, then the claim is that the composition is continuous, okay? And this is just a side note. We will come to this on thing in the functional analysis crash course. Is that like the space of complex valued functions, they form what we call C-star algebra. This is very important thing. We'll come back to this. And here's another proposition. This one is a little bit harder. So, but you can try this. If F is a continuous map and A is a subset of X, then the restriction of A, which is essentially you restrict the map only from the domain of it to be from A to Y, is also continuous. Okay. Okay. So another important notion that's built on top of continuous maps, topology is all about continuity. Okay, is that of homeomorphisms. Okay. And this is not the end of it. We will come back to this again once we get to the metric topology and also to manifolds. Okay, but at the moment, because we are in the general topology, we'll give the abstract definition, right? So two topological spaces, a continuous map. So homeomorphism needs to be continuous. Okay, so it's a continuous map. It is homeomorphism if it is bijective, right? Set theory 101, you know what a bijective map is. And most importantly, if the inverse of it is also continuous, okay? If that's the case, then it's a homeomorphism, okay? So that's essentially what homeomorphism is, a bijective continuous map whose inverse is also continuous, okay? And this is just like for those of you who have done like linear algebra stuff that we did finite dimensional vector spaces. This is the same. So we write if two spaces are homeomorphic. So homeomorphisms are like the isomorphisms, the counterparts of isomorphisms. Okay. So when two spaces are when there exists an isomorphism between them, we write like this. Okay. And you can see this is an equivalent relation also. If X is isomorphic to Y and Y is isomorphic to Z, then X is also isomorphic to Z. Okay. Now, there's something I would like to think. This is more of a point of to start a discussion that we will not have here. We'll have later in the manifold section potentially. In linear algebra, for example, when two finite dimensional vector spaces have the same dimension, that it follows immediately that they must be isomorphic. Okay, so the moment you prove that they have the same dimension, so they think so. The dimension is like an invariant, is an intrinsic property of linear spaces. Okay. Now the question is, are there any intrinsic topological properties so that when you are given two topological spaces, you don't need to try to find out whether there is a homeomorphism between them? You will say, because of this property, they must be homeomorphic. You will see as we go along, just bear this, that this is actually a very tricky question in terms of topological spaces. It's very hard. Okay, I won't answer now because there are some topological properties that we will define in the next in the metric topology section, and then I will be we'll come back to this question to see whether the topological properties that we will work with, whether they are intrinsic enough to be able to help us classify topological spaces. Okay, you will see this is a very very tricky question. Okay. Now, you won't be able to see this for now, for most of you, but homeomorphisms are essentially the reason why topologists, for topologists, for example, they say the donuts and the cup are the same thing. It's because of homeomorphism, okay? So in a nutshell, you can think of two topological spaces, okay? Just think shapes, okay? A donut is a shape. They are homeomorphic if you can continuously deform them into one, from one to the other without cutting or gluing. Okay, so this tells you that when you can draw a topological object, when you can draw them and see them or print them with a 3D printer or whatever, it can give you can have a picture, pretty much a decent intuition to whether the two objects are homeomorphic, because you can look at, okay, if I want to deform this to the other one, do I have to cut it? Do I have to do this? Do I have to glue it? If you do, then they are not homeomorphic. If you don't, you are able to do without cutting, without the thing, then it means that they are homeomorphic. Now the tricky thing is when you are not able to draw it, like say in the case of higher dimensions, for instance, or when you are not able to to print them, like physically to see stuff, which is most of the times for useful when you go to higher dimensions, then you need new toolkits in order to do that. So your eyes cannot help you. This is where algebraic topology stuff comes into place, things like homotopy theory and these things. Okay, so now, based on what I just said, who thinks a sphere can be homeomorphic to a donut? We'll come back to this again because we haven't really defined. No? Okay, so everyone says no. You can see why, right? Because if you were to take to deform a sphere into donuts, you will make a mess, right? You have to create a hole on it, right? So yeah, so you're right. Okay, cool. Now this is it. I told you we wouldn't, even though we were late, we wouldn't go through, over. So the reference study materials that I would recommend again is Moncrief's, the thing, by the way, who found the thing? Just in case, I could maybe try to find another reference for you guys to practice. Who found Moncrief's very difficult? Is it easy to follow? Is that a no? Someone said no. Moncrief's was not. Is it easy to follow? Is that a yes, Soham? Easy to follow, I guess.
Yes, at least for me it was.
Okay, that was for the creator. Thank you, Amir, for the thing. Yeah, I told you today I'm like a confused.com. Okay, so everyone in principle are happy to continue with Moncrief's. Okay, in the next segment, actually, I will give another recommendation. The same with the thing when we reach the manifold section, I will give another reference. Okay, now. I know that some of you, especially those of you coming from engineering, this is all like mumbo jumbo stuff, as our American friends say. It's very hard to see, all this. Okay, you already have a hint that this has applications in things like, topological data analysis, in, geometric deep learning, quantum, blah, blah, blah. So someone, a friend of, a colleague of mine, recommended this, especially for those of you who are coming from engineering background. Have a look at this book, Planning Algorithms. This is very interesting because a lot of the concept that we will be going through in topological stuff, find the thing they are referencing here, in concrete use cases. Okay, so this might be very very useful to those of you coming from engineering. Computer science type of background. You can download this for free. I'm afraid I cannot publicly put where you can download it. If you do a quick search, you will. I'm pretty sure you will find it. If not, ping me on Discord. I can. I'll see if I can get you a link where you can download this. Yeah, so for free. Yeah, so that's one of the things that we try to do things for free nowadays, right? I mean, these it's like, I mean, you can also sell, buy a hard copy on Amazon and these things, but who reads physical books nowadays? It's like, I mean, there are some physical books that I still read and these things, but okay, I see CJ has shared a link. By the way, just to make it clear, I didn't pressure CJ to share the link, so he's exercising his free will. Yeah. Okay, cool. Now, another thing before we go to part C is, the slides will be available on GitHub, and you can watch the replay of this. I will actually split the segments into different parts, especially today. Like it makes more sense today, even more, because the interruptions that we had because of my technical issues. And please join us on Discord, and organize yourself in like a self-study groups, especially those of you on the same time zone. Okay. And yeah, follow us on Twitter and LinkedIn for announcements that we will do. Okay. Now, this is time now for the lecture gap stuff. Let me create another poll, whether you want 2 weeks or 1 week gap. So let me see. I should have written this actually before. Sorry for that. I promise we will finish on the hour. When would you like? When would you like? Lecture 3 B. Option 1, check. Option 1, the 23rd, July 23rd. Friday, July 23rd. Option 2, Friday, July 30th. Okay. Now, some of you, someone said to me, like some of you were having like the Qiskit summer school or something. So, I don't want to influence your stuff, but it seems like obvious that it makes sense, 2 weeks. Okay, so we have a vote. Please vote on the poll, because you will dictate whether we'll have a session next week or the week after. July the 30th. So I only have 3 votes so far. I need more, huh? In fact, how many people are now? Yeah. Okay. Okay, so shall we say, because I can see like the majority wants on the thing, So 2 weeks gap then. So the next session where we will start with the metric topology section will be on Friday, July the 30th. There's someone who voted just for next week. Okay, let's see if there are more. Who else? Anyone wants to make a case for the others why we should, do 2 weeks? Because the thing, main motivation is not really because there is the thing. I couldn't care less about Qiskit. Sorry, about the Qiskit summer school. It's mainly to give you enough time for you to go through all these guys, these concepts that we've been that we define here, to go through the challenges and so on, right? Because otherwise you will find it very hard to follow the next sessions. Okay, so Amir likes to have 2 weeks between session. Yeah, especially I can imagine, especially if this is something new, because if you are new to this, I mean, it takes time to observe these abstract concepts. Okay, so okay, yeah, thank you, George. That's the thing. So that's why I was saying, join the Discord. Yeah, they were exchanging some stuff. That's great to see. Okay, good. So let's it's done there. Let's do the next session on Friday, July the 30th. Okay. So those of you who want to leave, they don't want to. Let me go back here. you don't want to think just 2 slides about about measurable spaces, you are free to go. You can also always watch the replay again. Okay, so let me go to part C.